to it. Welcome to the Explainer. Today, we're taking a completely fascinating journey, zooming all the way down into the fundamental building blocks of our universe. We aren't just skimming the surface of physics today, we're diving directly into the heart of matter itself. We're going to unpack the hidden mechanics behind atomic weight, the invisible, almost magical forces that keep everything from just flying apart, and the absolute sheer density packed into the tiniest spaces imaginable. Here is our roadmap for today. We'll start by calculating atomic weights, move into the tiny but heavy core, explore the strong nuclear force, reveal the secret to stability, and wrap it all up with mind-blowing nuclear density. We're going from macroscopic math all the way to the mind-bending realities hiding inside every single atom around us.
All right, Section 1, Calculating Atomic Weights.
Let's start with how we actually weigh an element. When you look at a periodic table, you might think those atomic weights are just flat single numbers. But actually, they aren't. An element's weight is essentially a carefully balanced, weighted average of its ingredients. To really get this, we need to talk about isotopes. An isotope is just an elemental variation. So that number on the periodic table, it's a calculated mix of all the different isotopic weights, based entirely on how naturally abundant each variation is out in the real world. Take a super familiar element like iron, atomic number 26. Iron is mostly made up of just one primary isotope, which is mass 56. That one accounts for a massive 91.72% of all iron. But, and this is key, those other variations like mass 54, 57, and even that tiny 0.28% of mass 58, they still exist. And because they exist, they still pull on that final average weight. So here is how that math actually plays out. You calculate the elemental atomic weight, which we call A, by taking each abundance fraction and multiplying it by its corresponding isotopic mass. You just divide the percentage by 100 to get your fraction, and then sum up the products for all four of iron's isotopes. Do that, and boom, we arrive at our extremely precise atomic weight of 55.846817 atomic mass units. It is a perfect weighted average. Moving right along to Section 2, the tiny, heavy core. Where is the mass? So we know how to weigh an atom now, but where exactly is all that weight physically sitting? To grasp this, you kind of have to completely reframe your mental picture of matter. The distance from the center of the nucleus all the way out to the outermost electron orbit is vast. Seriously, picture an atom as this huge, largely unoccupied space, with a minuscule microscopic dot right in the dead center holding practically all of the weight. The total atomic size dwarfs the nuclear size. And why is the center so ridiculously heavy? Well, look at the players involved. A neutron is slightly heavier than a proton, sure, but the real shocker is the electron. An electron is so incredibly light compared to a nucleon. It's only about 1/2000th of the mass. Because of that, the atom's mass is essentially just the nucleus. Those orbiting electrons, they contribute virtually nothing to the overall weight. And we can actually map out the physical size of this heavy core using the nuclear radius formula. It's R equals R sub 0 times A to the power of 1/3. This simple equation just tells us that the volume of a nucleus is directly proportional to its mass. As you add mass, represented by A, the nucleus grows. And it's governed by that tiny constant of proportionality, R sub 0, which sits at roughly 1.2 femtometers. Just to put that in perspective, a femtometer is a quadrillionth of a meter. It's unbelievably small. Which brings us to Section 3, the strong nuclear force, holding it all together. Now, this is where things get incredibly dramatic. We have this tiny, ultra-heavy nucleus packed tight with protons and neutrons. But wait a second. Here is the massive elephant in the room. Basic electrostatic rules dictate that positive repels positive, right? So how does a tiny nucleus hold so many positively charged protons together without just violently blowing apart? Why does matter even exist at all? The answer to that paradox is a profoundly powerful quantum concept called the strong nuclear force. Think of it as the ultimate cosmic glue. It has three defining features. First, it's effective only at an extremely short range, less than 10 femtometers. Second, it is universally attractive between all nucleons. Protons attract protons, neutrons attract neutrons, protons attract neutrons, the whole shebang. And third, and most importantly, it is vastly larger than electrostatic repulsion. It literally overpowers that repulsive push, but only as long as the particles are super close to each other. This short-range force is exactly what perplexed physicists for so long. Every single nucleon is pulling on every other nucleon. That means a proton is attracting another proton, directly fighting against its own natural electrostatic urge to push away. But remember, this massive attractive power comes with a strict condition. It only works if they stay within that tiny 10 femtometer boundary. If they step outside that boundary, the magic glue disappears entirely. Section 4. The secret to stability. Battling repulsion. So naturally, you have to ask, what happens when an atom gets bigger and those internal distances start stretching beyond that magic boundary? Well, as the mass of the nucleus increases, its physical size increases. When it grows too large, that short-range nuclear glue rapidly decreases and weakens. Suddenly, the underlying electrostatic repulsion between all those protons rears its ugly head and takes over. This epic internal battle between short-range attraction and long-range repulsion creates instability, and that instability is what leads to the fascinating phenomenon of radioactivity. So how do heavy elements survive at all? Nature has a brilliant workaround here, and it relies entirely on neutrons acting as a stabilizing buffer. Because neutrons have mass, but zero charge, they respond beautifully to the strong nuclear force, adding a ton of attractive glue to the nucleus. But, crucial point here, they don't add to the electrostatic repulsion because they aren't positively charged. They are the perfect peacemakers. Because of this incredibly delicate balance, if you exclude a few of the lighter elements, you absolutely must have a much larger proportion of neutrons to keep a heavy nucleus from flying apart. In a heavy, stable nucleus, the protons are just a smaller piece of the pie because they bring both attraction and that dangerous repulsion. Neutrons have to be the larger slice to flood the entire system with pure attractive force and keep the whole structure sound. All right, our final stop, Section 5, mind-blowing nuclear density. We've talked about the math, the warring forces, the stabilizing neutrons. Now let's look at the sheer physical reality of packing all this mass into such a tiny space. The density of nuclear matter is an exceptionally massive number, far, far beyond anything we experience in daily life. We're talking 10 to the 14th power grams per cubic centimeter, or 10 to the 17th power kilograms per cubic meter. To put that incomprehensible concentration into perspective, that's literally like cramming the entire mass of Mount Everest into a single sugar cube. No way, right? It's mind-boggling. But here is the truly fascinating part about this extreme environment. Because the nuclear mass and the nuclear volume are independently proportional to the mass number, A, they effectively cancel each other out in the density equation. What does that mean for us? It means that whether you're looking at a tiny helium atom or a massive uranium atom, the staggering density remains entirely constant. Nuclear density doesn't depend on A at all. It is a universal constant of atomic structure. Which leaves us with a pretty provocative thought to end on. If we, and everything around us, are made of atoms that are mostly empty, unoccupied space, yet holding these unimaginably dense microscopic cores bound by fiercely powerful short-range forces, what does that actually say about the true nature of the physical world we touch every day? The solid objects we feel are really nothing more than illusions created by forces in empty space. It completely changes how you view reality, doesn't it? Thank you so much for joining me on this deep dive into the atomic core. Keep wondering, keep exploring, and I'll see you on the next explainer.